let's get started. So we have done the warm-up of the previous chapter where we've explored various aspects of integrating a complex valued function of a real variable over, over contours and such. But now, finally, chapter 4 is upon us, and we have the genuine, full-blown definition of the complex integral. So I start the chapter with a quote from a letter from Gauss to Bessel in 1811. And basically what this quote says is that, hey, if you think about the integral of a complex quantity, a lot of the times if you go around in a circle, it's just going to be 0. But if you go around in a circle and the thing you're going around a circle of, if it's infinity somewhere in the middle, it doesn't need to be 0 anymore. So Gauss understood all of this, in 1811. It's a fascinating, I think, letter to read, because it predates the major publications by Koshi on complex analysis some decade later. So here it is. Here's the definition of the complex integral. So complex line integral. So the integral of f of z dz over a curve gamma is equal to the limit as n goes to infinity of the sum j equals 1 to n of f of zj minus zj minus 1. So just what's the setup here? The setup here is that gamma is a mapping from, say, A to B to the complexes where smooth path. All right. And we have z0, z1, zn in the image of the path, the trace, as we called it, of the path. And correspondingly, parameter values a less than or equal to? Fine, less than or equal to t0, less than t1, less than tn. I usually think of tn and t0 as equal to a and b, respectively. Here, gamma of t sub I is equal to z sub I, or rather j, for j equals to 0, n, all right? And so just to draw a picture of what's going on, the idea is we've got this, smooth path, right? And we're finding points in it, all right? So I'm just going to assume that z0 is gamma of A, right? And then z1 is gamma of t1. See, this is z2, gamma of t2, da-da-da. At some point there's a break, let's say. Keeps going and going and going, and zn is gamma of tn. All right. So that's the smooth curve, and what is this? What is this? The zj minus 1. What is that? You could look at that as, of course, like delta z, right? Maybe you could call it delta z, zj, perhaps. So, like here, this right here, from here to here, would be delta z1. Then from here to here, it's delta z2, right? Finally, over here, delta zn, right? So does it make sense that this would be a reasonable definition for the complex line integral? I mean, just like the Riemann integral for Calc 1, right? It's just instead of doing delta x's, you're doing delta z's, right? So you kind of expect that the answer is, in general, a complex number, right? But anyway, here's a potential definition for the complex integrals. This. Now,
Since we have x like as a always standing thing, like we're like just changing that, like where we're taking the the sum of rectangles, quote unquote, we're just making that delta z line. We're taking that as the integration.
no rectangles here. Each like f of zj times delta zj is a complex number. So it's not it's not an area we're calculating. In fact, so when you look at this, okay, so if you just take what I've wrote, so we're taking the limit as n goes to infinity. That's the integral, right? So if you just sort through this, what you're actually doing is integrating, right, from a to b, f of gamma of t times d gamma dt. Like that's what this integration is if we put it back in terms of the language of the previous chapter. See, because so for each time interval, you can pick, by the mean value theorem, you can pick a time in between, a sample time, such that basically you've got your delta zj, right, is equal to d gamma dt at some time, let's say zj star, times delta t, right? So this is the mean value theorem. Assuming that the curve is smooth, you can pick, some time, I should say tj here. Well, okay, fine, see. The point is this zj star is an element of, fine, technically zj star would be like gamma of tj star, where this tj minus 1 is less than or equal to tj star is less than tj. Really didn't want to get into all this. The point is, you can convert this to the limit as n goes to infinity of, f of gamma of tj times d gamma dt of gamma of tj delta t, and that is just literally this integral. All right. But what is that? Well, this, right, we can say further, this is the integral over gamma, right, of u plus iv times what? Times dx dt plus dy plus I dy dt. I guess I'm still integrating from over t at the moment, a to b, right? Using the other notation, dropping the of gamma of t there for convenience. And what do you got? You've really just got the integral over the curve of u plus iv dx plus I times the integral of u plus iv dy. Where those are the kind of integrals we talked about in the last chapter. And so, of course, you could just then, this is straight up an integral. We could break it down further. This would be the integral over gamma of u dx minus v dy plus I times the integral over gamma of v dx plus u dy, right? So really, any of these statements could be taken as the definition of the complex integral over a smooth curve, right? But the last integral I think the last one is useful because this gives us some kind of understanding of what the complex integral is. You could say it this: it's calculating the work done over gamma of two different vector fields. This one is the work done by the vector field u comma minus v. This one is the work done by the vector field v comma u. So the work plus I times the work done by this vector field plus I times the work done by that vector field over gamma if you want an interpretation. That's not how I think of it. My point to you is it's not something directly geometric, right? It's something more abstract than that, right? It's not the area under a curve. It's something else. So there it is. Now, notice that the original thing, we could also use the notation. So, notation, you could literally just say dz is dx plus I dy. That's a pretty good guide. Then if we do the integral of u plus iv dz over a curve, right? That's the integral over u plus iv dx plus I dy, which when you multiply it out, it gets you exactly back to here, okay? So the notation is very forgiving if we just introduce dz as dx plus I dy and follow through formally. It's exactly what you like. Now, suppose you don't have a smooth curve, but you have an arc. What's an arc? So union of finitely many smooth curves, yeah? Right? Let's say gamma 1, gamma 2, dot gamma n. So then if we say gamma arc, right, then the integral over gamma of f dz would just be the sum I equals 1 to n of the integral over each of these guys. I'll do j equals 1 to n of gamma j of f dz. So yeah, we just add them up. Finitely many is important. You can't have infinitely many discontinuities. I'm not going to try to describe a complex integral for such things. All right, a curve has to be nice enough that you can express it as finitely many smooth curves. I'm not saying it's not possible to define something for more than finitely many. I'm just saying it's not in my wheelhouse here in this course. Okay, so that's the first thing. First example. Let's let gamma from 0 to pi to the unit circle, to C be the unit circle, right? Gamma of t equals e to the it, all right? And let's calculate the integral over gamma of dz over z. All right? So how do we do that? Basically, you calculate dz as d gamma dt dt. Let me repeat that. dz is d gamma dt dt. So, in other words, this is really z for the curve, right? So we get dz is I e to the it dt. Right? Z equals to this for the curve gamma. And so the definition basically just says, set z equal to the parameterization for the curve and plug it in here. Integrate over the parameter values. Here, 0 to 2 pi. So my dz is I e to the it dt. And here, e to the it, because that's what z is equal to. The e to the it's cancel. And we've got I integral of dt from 0 to 2 pi, which is just what? T, evaluate I times t, 0 to 2 pi, which is what? Yeah, 2 pi I. So the integral of the 1 over z function is 2 pi I over the unit circle. Okay. Example 2. So if we have a line segment, go from P to Q, line segment, right? So a typical point on this would be gamma of t equal to what? Equal to P plus T times Q minus P, right? That's how we parameterize a line segment. So that's my z for this curve, right? So what's dz? dz would just be Q minus P times dt in this case, right? And so we can calculate, if I call this curve C, all right, integral over C, which I've been calling gamma up to this point, but you know, C is the trace of gamma. And if I want to integrate z to the n dz, and here n is not equal to minus 1. We did n equals to minus 1 in example 1. right, in the case of a circle. Well, then this would be what? This would be, how would that go? Integral from 0 to 1 of p plus t times q minus p to the n power times q minus p dt. But basically, you can make a u substitution, right, to do this integral. See? So this is, by the way, this is for 0 less than t less than 1, right? That's the standard trick that parameterizes the line segment. So if I let this thing be quote unquote u, well, this is du, right? So we get what? We get I might have made a mistake. Oh, no, I didn't. Well, the thing is, if I gotta be careful here. We get p plus t times q minus p over n plus 1, this to the n plus 1 power, evaluated from 0 to 1. Yep. I got to be careful. If I make a u substitution but I don't change the bounds, it could be deceiving. So I'm not actually going to write out the, I'm just pointing out that that's the kind of integral we're doing here. And so what you get is 1 over n plus 1 times what? If I plug in 1, I get q, right? If I plug in 0, I get p. So there you go. This is pretty neat, right? Because it says that the complex integral works just like the real integral, right? If we integrate from p to q, z to the n, we just get q to the n plus 1 minus p to the n plus 1 divided by n plus 1. All right. So we already know, lots of calculus for these kinds of integrals. Here's another example. Let's see here. If I was going to integrate over gamma equal the line segment from p to q again, but this time z to a complex power dz. All right. Well, again, it's just the integral from 0 to 1 of p plus tv p plus tv to the c times v dt. So what I've done to make life easier in terms of writing is I've let v equal to q minus p for the sake of example 3. If I introduced that notation in example 2, it would have made that one easier too, right? So here c is a complex power, right? So in order for this calculation to make sense, I have to assume that the line segment is somewhere where we have defined, where that line segment doesn't cross the branch for our branch cut of the power. So like, for example, if p and q were like this, right, and maybe this is the, over here is the negative real axis, right? If that's the case, if that's where the negative real axis is, in other words, if PQ is a subset of the slit complex plane, then we could just use the principal power, right? And in any event, same calculation then goes through by the calculus that we've worked out before, and we would have, 1 over c plus 1 q to the c plus 1 minus p to the c plus 1. Assuming what? Assuming c is not equal to minus 1. All right. Now, I should talk a little bit more about example 1. Like my example 4 is my, example 6 actually, is my example 1, I think. And do you see why that is? Well, I'm not saying you have to look at example 6, but let me just talk about it here. What is 1 over z equal to? Yeah, z is minus 1. It's 1 over x plus iy, right? Which is equal to x minus iy over what? X squared plus y squared, right? And so when we're integrating dz over z, what are we doing? We're calculating the integral of x minus iy over x squared plus y squared times what? Times dx plus I dy, right? So that is explicitly the integral over gamma, the unit circle in this case, of what? X dx plus y dy over x squared plus y squared plus I times the integral over gamma of, what is it here? X dy minus y dx over x squared plus y squared. My point to you is that we have previously integrated x dy minus y dx over the circle in the previous chapter. We spent some time on this example because this guy right here, right, was essentially the integral over gamma of d theta, is what I explained it as last time. Yeah, and we saw that that was 2 pi. So what I'd like to point out to you is the calculation we just did in black has done everything we did in the previous chapter and more, right? Because what we've done by showing the integral of 1 over dz is 2 pi I, we've shown two things. We've shown, one thing we've shown is that the integral of this piece, right, is equal to 2 pi. See, because the imaginary part of this has to match the imaginary part of that. So this, you can read off that this is 2 pi from that. The other thing we've shown is that the integral of this guy right here is 0. Because the real part of that is 0, which means that the integral of this real integral is 0. So this actually illustrates something else. Check this out. So is it necessarily the case that when you integrate something which has an infinity for the expression you're integrating, right? Is it necessarily that that's non-zero when you go around? You're going around infinity here, right? Infinity's in the middle of the circle, right? Circle, here's 0. That's inside the circle, gamma. And yet this integral is 0 despite the fact that it had infinity in the middle, right? So it's not automatic that when we have an integral around something that diverges, it's necessarily going to be non-trivial. It doesn't have to happen. It's already in this example. Okay. Moving on here. This calculation is a calculation of note, the one we're about to do. Oh, curses. I mustn't erase this, though. So next up, example 4.1.7. If we integrate over the circle of radius r centered at z0 in the counterclockwise fashion, the quantity z minus z0 to the m dz, we can show that it's equal to either 2 pi I for m equal to minus 1, or it's 0 for m not equal to minus 1. And the calculation of that is simply this. So what's z equal to here? For this curve, we've got z is equal to z naught plus r e to the it, 0 less than or equal to t less than or equal to 2 pi. That parametrizes that circle in the counterclockwise fashion. So what's z minus z naught is equal to what then? Just re to the it, right? And so when we're doing the integral of, over this curve, I'll call it gamma, of z minus z naught to the m dz, what we're facing is the integral from 0 to 2 pi of r e to the it raised to the m power times, well, I r e to the it dt. So if you tilt your head and squint, you see what you got there is I r to the m plus 1. And then we've got integral from 0 to 2 pi of e to the I, and then you got an m plus 1 t dt. So that gives us I r to the m plus 1 divided by m plus 1 times I. And then we've got e to the I times m plus 1 t evaluated from 0 to 2 pi. Now, for m not equal to minus 1, see, because the integral of the exponential is 1 over the argument of the exponential multiplying t times e to the, it's like the integral of e to the ax is 1 over a, e to the ax, right? By regular calculus. So by complex calculus, since it obeys the same chain rule, the same exponent, derivative of exponents, the exponential, right? All that same integration rule. We divide by the argument, which is I times m plus 1 here. But what happens when you plug in 0 and 2 pi into this? You get e to the 0, which is 1. What happens when you plug in the 2 pi? You get e to the I times m plus 1 times 2 pi. M plus 1 multiple of 2 pi. The exponential is still 1. You get 1 minus 1, which is 0. Now, in my notes, I express this in terms of sine and cosine. Perhaps that's more, understandable. But when does this calculation fail? The place where this calculation fails is when m equals 2 minus 1, right? And how about the m equals minus 1 case? Why is that 2 pi I? Well, that's essentially example 1. So we already went through that in example 1. But you can, when m equals minus 1, what happens is the e to the it here cancels, e to the minus it here cancels with e to the it here cancel, e to the it, and the r, 1 over r and the r cancel, and you're just left with integral of I dt, which is 2 pi I. So that's the m equals minus 1 case. Okay, now, so next up is the so-called ML theorem. So calculation, if we take the absolute value, it's going to be the modulus of the integral over gamma of f of z dt dz, right? That is equal to, I'm going to pass the limit outside the absolute value. I can do that because it's continuous, right? This. Right? Which I should have really just written, let me just write that as delta z. It's out of our misery, delta z. Right? Which then by the triangle inequality, But this is exactly equal to the integral over gamma of the modulus of f of z times the modulus of dz. And here I'm making a definition, actually. The integral of like f times modulus of dz over gamma. What this means is the integral over here, I'll do it in terms of a parameterization. Integral from a to b of f of gamma of t times the length of d gamma dt. You might recognize this more if I wrote it as the integral over gamma of f of gamma t times ds, where ds is the square root of dx dt squared plus dy dt squared dt. In other words, this is the integral with respect to arc length, right? So this calculation I just did is known as, well, it's an estimate. It gives us that the modulus of the integral is less than or equal to the arc length integral of the modulus of the function, right? So one more thing, if we know that the modulus of f of z is less than or equal to m for z in gamma, right? In other words, if our complex function is bounded by m, well, this is then less than or equal to the integral over gamma of m times the modulus of z, right? Which you could write as m times the integral over the modulus of dz. What is the integral? This is a fancy way of saying the integral of arc length over gamma, right? So dz, this is dz is modulus of dz is ds, okay? So that's just m times L, where L is equal to the integral of ds over gamma. It's the arc length, right? So this is the famed ML theorem. The ML theorem says that, in short, if we want to estimate the integral of a complex integral of f of z dz, well, it's less than or equal to a bound for the integrand times the length of the arc. So, theorem. That is actually how we calculate quite a few things in this course as we go on. Now, I give an alternate proof of the ML theorem, which is really quite beautiful. Not from me. I saw my advisor give it when I took complex analysis in 2005. It's in the notes on page 80. I would urge you to read through it. It's kind of neat. But I also would point out that this derivation is completely natural. And it's a lot of the reason I started with this as the definition, because with this as the definition, we get the ML theorem just by like pretty natural triangle inequalities parsed with a limit. The proof for the ML theorem that I give on page 80 is much more ingenious. Let me give you a standard example here. 4.1.11. So we'll let gamma r be half circle. So it's the circle of radius r that goes from r to minus r, all right? Half circle. And so we're going to talk about how to bound the integral over gamma r of dz over z squared plus 6. All right? So I guess first I should figure out what's a bound on z squared plus 6. 1 over the modulus of z squared plus 6, right? Less than or equal to what? It's less than or equal to 1 over the absolute value of the modulus of z squared minus 6. Using the triangle inequality, the reverse triangle inequality. Well, it's the other triangle inequality. I've made the denominator smaller. So this is larger than that, which makes this fraction smaller than that. But if we're on this arc, these arcs have what? These have modulus of z equal to r, right? So this is straight up equal to 1 over r squared minus 6 absolute value, right? Which is equal to 1 over r squared minus 6 if what? If r is greater than, say, the square root of 6, right? So let's assume we're in that case, r greater than the square root of 6. See? If we're in that case, we just found m. That's a bound right there. So here's my m. And so what we got is this is less than or equal to 1 over r squared minus 6, right? And what's the arc length? What's the arc length of a half circle of radius r?
Oh, the arc length is like 180 divided by...
You're doing it in degrees?
Yeah.
Oh, no.
Pi over the z-naught? Yeah, because that's where you take it.
So it would be 2 pi r, right?
Yeah.
2 pi r over 2, so we just get pi r, right? Pi r is the arc length here. So there you go. That's a bound for that integral. Now, actually doing this integral would be a pain, but there it is. And the cool thing here is what happens as r goes to infinity. This goes to 0 as r goes to infinity. So if we had the case where we were dealing with like an upper arc like this, where the radius goes to infinity, we'd be able to get that this is 0. And you notice that you could play similar games if you had like a cubic or a quartic or whatever. The thing is, it's a little bit more trouble, the inequality, but you can show essentially that as long as the degree of the denominator is 2 more than the degree of the numerator, then you can always prove this kind of integral goes to 0 as r goes to infinity through a similar argument. All right, so that's kind of neat. All right, that brings us to the fundamental theorem of calculus, parts 1 and 2 for complex integrals. All right? What do you think they are? Well, we talked about it for a complex valued function of a real variable, but we haven't talked about the integral of a complex valued function of a complex variable, and that's what we're doing now. That's why it's different than last week.
So, well, I still expect that the integral from a to b of f of z is, or f prime of z is going to be f of a minus f of b.
Oh no, I never moved the camera, did I? Well, fortunately, I didn't erase. You know, my bad. Sorry about that, peoples.
But yeah,
So let me summarize. What you're saying is going to be the same thing we already had in calculus 1,
yeah,
just with complex derivatives instead of,
yeah,
yeah.
and then maybe some funny quirks.
So definition, f of z is primitive for f of z on D if big F prime of z is equal to f of z for all z and D. In other words, primitive is another word for what do we call it? We call it an antiderivative, right? Primitive is another word for antiderivative. So we have 2 theorems in this section. FTC II, as I call it, and I think Gamelin has the numbering otherwise. You know, some calculus books have them numbered 1 and 2, and others have them numbered in the opposite way. But anyway, here it is. The integral over gamma of f of z dz is f of b minus f of a. And here this is a gamma, is a what? You know, path from from A to B inside D, right? On which f prime of z is equal to little f of z, all right? That's the fine print there. And FTC I let D be star-shaped right? And f of z holomorphic on D, all right, then f of z equal to the integral from z naught to z of f of zeta d zeta is a primitive for f. On D. Now, the proof for both of these theorems, it's pretty easy given what we already know from the last chapter. All right. So let's see here. So let's look at the proof of FTC II. How's that going to go? So we know that f prime of z, big F prime of z, right, is equal to f of z, right? Which essentially means that df dz is still f of z, right? So therefore, df is f of z dz. So when you're integrating f of z dz over gamma, you're really just integrating the total differential of the primitive. But we proved the FTC for these kind of integrals, right? From the differential of a complex valued function. So I guess I'm cheating here to write this like this, but I guess this is a cheat. This is a cheat. This is a cheat. That's not a real proof, is it? Not really. I think I'm probably assuming what I'm trying to prove here in this. Let's see if we could do better. Oh, I've said do better. Oh, I feel so dirty. Ugh. Let's try this again here. So let's see here. So f prime of z is f of z, right? So that means that this is equal to partial f partial x, but it's also equal to minus I partial f partial y, right? By the Cauchy-Riemann equations. And so when we're integrating f of z dz, we're actually integrating partial f partial x times dx plus I dy, right? But that's the integral of partial f partial x dx plus I times partial f partial y, partial x dy, right? But of course, this tells you what? This is what? Another way you could write this is partial f partial y equals to what? I partial f partial x, right? So this is, in fact, partial f partial y. So what we have is the integral of partial f partial x dx plus partial f partial y dy over gamma, right? And okay, so now you see why I was right to write the integral over gamma of df, right? And then again, by the FTC we had in the previous chapter, that's f of b minus f of a. All right. I'm going to move the proof of FTC1 to next time. Let's finish class with an example instead, okay? Okay, so suppose we look at, this is kind of a delicate argument. So we're going to look at the arc, that goes from here to here. So here's the circle. So we're going to call it gamma r, gamma epsilon r. And so where it's going to is it's going all the way over here to like what? To like pi minus epsilon, and over here to, you know, minus pi plus epsilon. Right? So that's the angle it's going over, all right? But otherwise, so gamma of r is r, you know, e to the it for pi minus epsilon, for minus pi plus epsilon less than or equal to t, less than or equal to pi minus epsilon. And here I have in mind epsilon being a small positive quantity, right? So if I choose that domain for my path, I've been careful to not cross through the branch cut for the principal logarithm, right? And so if I look at f of z equal to 1 over z, right, it's equal to d dz of the principal log of z for z in the slit complex plane, right? In other words, log of z is a primitive for 1 over z for my carefully constructed, not quite a circle. And so this tells us that the integral, right, over gamma epsilon r of dz over z is what? So we're looking at, well, it's log, right? Log of what? Log of gamma sub r of epsilon of, you know, pi minus epsilon minus log of gamma sub r epsilon of epsilon minus pi, yeah?
Oh, but that's FA minus FT, right?
Yeah. But what is the log of that?
What are we saying? Gamma r epsilon? I thought that was like a map. I thought that was a map.
So what we're dealing with then is the natural log of r plus I times pi minus epsilon minus the natural log of r plus I times epsilon minus pi. Of course, the log r's cancel, yeah? And what we're left with is 2 pi I minus what? Minus 2I epsilon, I think. So what happens as we take the limit as epsilon goes to 0? We get what?
As epsilon goes to 0,
As that, we get 2 pi I. Does that make sense? I think it does, because we proved that the integral around the circle, right? Well, we did units. We did circle radius r, didn't we? Yeah. Example 1 today. We showed that this was 2 pi by direct calculation. Now I'm showing that it can also be understood to be 0 if we're careful to treat our branch cut with respect, which means that we have to approach it but not cross it because of that 2 pi jump. That 2 pi jump is where that 2 pi I is coming from for the integral of dz over z. Anyway, so next time we will talk about, you know, FTC I and perhaps more interestingly, Koshi's theorem. So this is the first of several theorems of Koshi. There's Koshi's theorem, there's Koshi's integral formula, then there's Koshi's generalized integral formula. So just beware, we have to keep those separate. Thanks, guys.